Okay, I'd like to welcome everybody to the South Dakota Local Foods Conference. I am Cindy Toll, and I am on the board of the South Dakota Specialty.
I think we just lost Cindy, but I'm glad she got to introduce herself. The South Dakota Specialty Producers have been putting this conference together all year, and the board has really been working and supportive of our efforts to make sure that we bring this online and have a safe and fun and really good experience for everyone. And we need to thank all of our sponsors tonight coming into this. The USDA Natural Resources Conservation Service is bringing you David Montgomery's keynote speech tonight. A big thanks goes out to them for bringing him here. We also need to thank Monument Health of Rapid City and the Audubon Dakota. And I should have video.
Yep, we can see you, Kathleen.
Great. I've got Sturgis Meats, of course, and Evergreen Ranch for a sponsor as well. Glory Garden here in Sioux Falls has sponsored us, and the Bell Valley Ancient Grains, as well as the South Dakota Soil Coalition. So big thanks go out to all of those sponsors who made this event possible, made this happen tonight. With that, I will introduce Andrew Thomason, and he is with the NRCS, and he is going to be introducing your keynote tonight. Hi, Andrew.
Hello. So hello, everyone. I have the pleasure of introducing our keynote tonight. He's a MacArthur Fellow and a professor of geomorphology at the University of Washington. He studies landscape evolution and the effects of geological processes on ecological systems and human societies. He's had award-winning science books. He's been featured in documentaries on network and cable news, and a host of TV and radio programs. He has a couple of books, Dirt, The Hidden Half of Nature, and Growing a Revolution, which will be in the keynote today. Just keep in mind, questions will be asked, will be answered at the end of the presentation, and you will ask them at the Q&A down at the bottom. But with that said, I'll introduce David Montgomery.
All right, well, Andrew, thank you very much. And thank you all for inviting me to zoom in this strange new world that we live in and share with you some of the work that I've been doing on looking at soils for the last few years. So I'm going to share my screen and get started with what I want to talk about. And I am a geologist, so I'm not exactly the kind of person who you would expect to write a number of books about soils, soil fertility, the importance of soils, and the ongoing endeavor of civilizations. But looking back over the last 10 years, I find that's what I've done. So what I want to do with you today is to share with you the story of how I've come to look at soils in a different way through the explorations that led to the 3 books that are on the screen now. Dirt, the Erosion of Civilizations is a book that looks back at the history of past civilizations and the role that land degradation, soil degradation has played in the course and fate of human societies. It's the kind of book you might expect a geologist to write. It looks back at history. And I got into it because I had traveled around the world looking at soil erosion under natural circumstances. A lot of what I work on as a geologist, I'm the kind of geologist who studies geomorphology, what the processes that shape the surface features of the earth. So erosion is something I was trained to look at and looked at it for years. And I started to notice correlations and patterns around the world about the state of soils in different regions and the degree of impoverishment of civilizations in areas that had formerly been very prosperous. So that was what got me into thinking about soils in a way that I wasn't really trained as a geologist to do, although I was trained to think about soils and how they form. I was taught to look at the rocks underneath as the good stuff. It took me a while to come around to realize just how important and interesting soils are and what opportunities restoring fertility to the world's soils offers humanity in the current century. That middle book up there, The Hidden Half of Nature, I wrote with my wife, Anne Baclay. She's a biologist. And when you think about what makes for healthy, fertile soil, you need the geological and you need the biological. It's putting them together that really makes healthy, fertile soils. And that book was explores the role of microbial life, the part of soil fertility that we have sort of forgot about for part of the 20th century and thinking about agriculture, but which turns out to be really, really, really important. And then Growing a Revolution takes the lessons of that first book and the science in the second book and applied it to the problem of how do we restore fertility to the world's soils on working via economically viable farms in different parts of the world. So I'm going to walk you through my sort of the evolution of my thought on this. And if you want to connect with either Anne or I, you can visit us and communicate with us through our website or our Twitter feed shown there at the bottom of the screen. But let me tell you a bit more about why it is a geologist would be concerned about the state of the world's soils. If you wanted the simple one sentence description of the post-glacial human relationship with the world, it's that we've degraded land in different parts of the world to our own detriment time and again through history. And it's a central thesis of Dirt, and I'll elaborate on that a little bit more. But if the first part of this talk turns out to sound a little depressing, the look back is a little depressing in the way that societies have treated their land. But we're going to get optimistic by the end, and we're going to turn this arrow around by the time we get to the end to look at how farming practices can restore fertility to the world's farmlands as a consequence of intensive farming practices that are profitable. So let me first set the stage with why a geologist would think that soil degradation is a global problem. This map is the UN's map of soil degradation from a few years back, and it's painting with a really broad brush, but you'll notice there's an awful lot of orange and that red color that on the map. Pay more attention to the red color. Those are the areas of the world where there have been some serious degradation to topsoil to the degree that it could affect agronomic productivity without supplemental support from intensive agrochemical fertilization. So in other words, the problem of soil degradation is a global problem, but how big a problem is it? I'll get there in a moment, but I want to remember to point out that you can go into any one of those red zones on this map, and you can find farms that are turning around the story that this map tells at a broad scale. There's examples of regenerative farms around the world that are building healthy, fertile soils as a consequence of farming practices, and that's where we're going by the end of this talk. But I want to start with the framing of the global problem of land degradation, because it truly is a really big global problem that doesn't get anywhere as much attention as it deserves on either the national or international stage. David Pimental and colleagues at Cornell back in 1995 concluded that in the post-Second World War world, at their time in the previous 40 years, between the 45 and 95, soil erosion and degradation degraded some 450 million hectares of arable land. That's about equivalent of 1/3 of all the world's cropland that we degraded over the course of about a century. Now, if you look at all other estimates of how much of the world's farmland has been degraded through the course of human history, what you come up with is usually about 1/4 to 1/3. So Pimentel's estimate may be a little on the high side for that one period. But if you look at it over the last 10,000 years, over the course of agricultural history, we've degraded something around 1/4 to 1/3 of the world's farmland to the point where it's been taken out of agricultural production. And in any way you look about or think about how we will feed the world of the future, if that land was still in peak producing condition, we'd have a much easier time of doing it. But the problem of land degradation is not simply ancient history. It's not a problem that has been completely solved. 5 years ago, the UN Global State of the Soil Assessment, one of the first global assessments of the state of topsoil around the world, concluded that humanity, the global us, we're losing about 0.3% of our global food production capacity each and every year to soil erosion and soil degradation, the loss of soil organic matter, the degradation of soil biology. That 0.3% a year, that doesn't sound like a terribly fast rate when you think about it just on the face of it. Unless if you're a geologist, you see that and go, wow, that means that in 100 years, a century, which to a geologist is kind of a blink, that's just a down payment on tomorrow. It turns into 30%. And so we're on track this century with our conventional agricultural methods to degrade another third of the world's cropland at a time when we actually need to increase agricultural productivity. Those trends are working in opposition to one another. And that's the kind of issue that motivated the concern that I had in researching and writing the Dirt Book. Now, to be fair, I also thought it would be a wonderful excuse in looking at the sort of the archaeology of ancient civilizations to travel around the world and have a look at some of the places that would feature in the story. But there was this other parallel concern, a big concern in terms of the state of the world's soils and what that meant for the future of agriculture. And since I'm a geologist, I looked back through history and looked at the role that soil degradation played in ancient civilizations. And what you find when you dig into that is that soil degradation and the loss of the soil and the degradation of soil fertility played a role in the demise of many ancient civilizations, from Neolithic or Bronze Age Europe to classical Greece, Rome, southern United States, Central America, and more that I document in the book. But what I took away from researching and writing that book was more than just the story of those individual places, but the common themes that ran through the stories in those places. And one of the ones that I found most surprising, given my background and training, is that the story that one found was not the story that was usually in environmental history textbooks, where what you will usually read is that deforestation caused erosion that helped to undermine societies. And the idea that soil degradation played a role in the decline of ancient civilizations is not a new idea. You can trace the idea, actually, as we will, all the way back to the classical Greek philosopher Plato. But what I found very interesting was that it wasn't so much the axe as it was the plow that followed that was the root cause of the land degradation that sort of drove the process. So what was it about the invention of the plow? It fundamentally altered the balance between soil production and soil erosion, dramatically increasing the pace of soil erosion. Now you can think about soil as something that's formed from breaking up of rocks and mixing that with organic matter and living organisms, as we'll get to. But it also can be viewed as a system that is lost. So it's produced from breaking down rocks and making new soil. It's lost through erosion. And if you look at that as a balance, the amount of soil that we have in a landscape reflects the balance between those inputs, the soil production, and the losses, soil erosion. And you can think about the analogy, of your own bank account, but where we have income and we have expenses. And we all know that if you spend money faster than you make it for long enough, you can burn through your savings. That's essentially the story of human civilizations, time and again, not all of them, as we'll get to, but many of them. Over the course of their history, if you think of soil as the natural capital that allows agricultural civilizations to thrive and feed their population and grow, societies that erode or degrade their soil faster than it's being rebuilt are literally burning through their natural capital. And it then becomes a question of, well, how long can that go on before a society starts to really feel the bite of that difference? That's what motivated me to look into the problem of soil erosion and degradation in past societies. Now I'm going to spare you all the civilizations that I talk about in the Dirt Book. I'm a professor. I could talk till midnight about all that kind of stuff, but I'm just going to start with classical Greece, because there was a lot of work done in the 80s and 90s on the geoarchaeology, the geology and archaeology integrated and looked at together in the Greek landscape. And what the scientists found was that cycles of erosion and soil formation in ancient Greece began really in the Bronze Age, several thousand years before the time of Christ, right after the introduction of plow-based agriculture. So the plow came from Asia Minor onto the Greek peninsula, and what was there at the time, this shows you a cross-section of a typical hillside in southern Greece, made by Tjeerd van Andel and Chris Reynolds, the geologist who actually taught my sophomore level geology course when I was an undergrad, and Chris Reynolds, an archaeologist, who they worked together in this landscape. And this is their reconstruction of what that landscape looked like immediately after deglaciation. So this is really at the dawn of the agricultural world in the Middle East. You had an open oak woodland. Ridgetop over here on the left, River Valley down there on the bottom, this lighter brown colors, the soil on the hillside. They had about 1 to 3 foot thick soil profile on the hillsides with sort of an open broken woodland. As when agriculture arrived, where do you think they started farming? Well, it wasn't on the ridge tops, it was down the valley bottoms, right? Because that was where it was relatively flat, easily worked ground with fertile soils proximal to sources of water. But as their population grew, farming and tillage worked its way up the field so that grain was grown sort of, ridge, valley bottom to ridge top after centuries at the peak of the Bronze Age. And what Van Andel and Reynolds documented was that led to a period of soil loss where the hillside soils ended up down in the valley bottoms, leaving bare rocky soils called maquis, where you can still find Bronze Age agricultural implements in places where you couldn't possibly grow wheat today. And the problem, of course, in this landscape is that if you take a thin soil and strip it off the hillsides and pile it up in the valley bottoms, what matters for this year's agricultural productivity isn't so much the total amount of soil on the landscape as is the surface area that's covered. So if you take a thin deposit and pile it all up in one place, you can't grow as much food. And this was a real problem in classical Greece. Van Andels and Reynolds, though, went a step further and looked at the human population density in different regions of southern Greece. And this shows you really the graph that started me off in terms of really thinking hard about this problem of land degradation and the course of civilizations, where what they've done is they've plotted the population density in this valley from about 6,000 BC, so not long after the start of agriculture, in points further to the east. When the plow arrived in the Bronze Age, the population went up, and then it crashed into a dark age before the age of classical Greece. The population rose again, crashed into another dark age, and it's risen again in the modern age. And of course, it begs the question of what's going to happen off to the right-hand side of the graph in the future, but we'll get to that in a minute. What I like to point out about this graph is that there's sort of two things I think are really interesting about it. One of them is fairly trivial, and that's the question of, well, okay, you've got these 3 cycles, a rise, decline, rise, decline, rise. Each time it gets to a higher number of people that you can support on the landscape, a bigger population density. And I think there's really no mystery behind that. We have better technology today than we had in the Bronze Age. So we can support more people per unit of land, whatever unit of measure you want to measure land in. We can support more people per sort of bit of land than we could back in the Bronze Age. But the question that really intrigued me about this graph is what sets the periodicity? Why a several thousand-year rise, a 1,000-year crash, another rise, another crash for 1,000 years? That kind of 1,000-year-ish kind of time scale to the pulse of civilizations was really intriguing to me. And there's very few places in the world that you can find where there's been 3 agricultural civilizations in the post-glacial world on the same bit of land. And it's even rarer to find a place where the geologists and archaeologists have already done the work that you can find a graph like this in one of their publications. So I got really interested in this and started looking at stuff in different societies around the world. But I also started looking into the history of this region. And what I found is that, when you think you've come up with a really good idea to explain, a pattern you see in science, you often go into the literature and you find that somebody beat you to the idea. Well, the idea that soil degradation impacts human societies, I don't take credit for that idea. Plato beat me to it by about 2,500 years. What you can find in one of Plato's dialogues, when he was he was writing at the crest of classical Greek civilization. So after that crash from the Bronze Age, he was on the second peak of agricultural civilizations in the Greek peninsula. He looked at the state of the landscape, and he was a very observant student of nature. He noticed things like the rivers that were flowing out of forests and entering the Mediterranean ran clear and had small deltas, small deposits of sediments at the river mouths. The rivers that were coming off of regularly plowed fields, intensively worked agricultural lands, were flowing muddy and had big deltas of sediment building out into the Mediterranean. And he noticed things like trees up on pillars on the edges of farmed fields, and pillars of soils rising, several feet up above plowed fields. And he realized that the trees had not pulled the earth up around the roots, but that the fields had eroded down around these old trees. And so he wrote that the rich, soft soil has all run away, leaving the land nothing but skin and bone. But in those days, the damage had not taken place. The hills had high crests. The rocky plain of Fellows was covered with rich soil, and the mountains are covered by thick woods, of which there are some traces today. He went on to basically describe how he thought that the process of soil loss from the landscape had degraded the ability of the Greek landscape to support a population that would allow them to field the large armies that Athens wanted in those days to repel invaders from the east. So Plato read these connections between human societies and the state of their land and the soil go back a long ways, and you can find a number of books through the years, through the last 150 years, really, that have made this case. There's a great book by some Soil Conservation Service employees called Topsoil and Civilization that I read as an undergraduate that seeded me to be thinking about these issues now decades later. But let's not just think that the problem of soil degradation is an ancient history problem. I'm going to pick on my home state of Washington now for a few minutes because I generally find it safer to pick on one's home state. I could show you slides from different places around the world to make the same point though, but this is a slide from the Palouse. It's the east region of eastern Washington, taken in about 1970, and it shows you a winter wheat field on some slopes that get fairly steep, but it illustrates the problem with the plow the way a geologist would look at it, because you don't see a crop out in the field at this point. They practiced a traditional wheat fallow rotation for many years, and notice also this is some 30 years after the Dust Bowl, and it illustrates the problem of what happens when you get rainfall on a freshly plowed field where the next crop or weeds hadn't come back to actually protect the land surface. All those little channels get carved into the surface. We call them rills. You can erase them with a single blast of the plow. But what happens is that if they keep recurring year after year, they can really add up to substantial erosion. This shows you an image on the edge of a field where it's again in eastern Washington in the Palouse, the same region I was just showing you, and it illustrates what can happen if those rills form year after year after year. This fence in the upper right-hand corner is a fence that the farmer built around their water cistern back in 1911 when the field was up at this at this level, and it was first plowed, and then nothing happened there for 50 years other than that wheat fallow rotation, so annual tillage, and sometimes it would rain and you'd get those kind of rills forming and the erosion would add up over time. So this photograph was taken in 1961 by Vern Kaiser, and it shows you the difference in the land surface elevation at the bottom of this hill over those 50 years. What you can't really see very well is this little black line right here. That's a 1 foot increment on a survey rod. That's kind of a little washed out in the negative. In other words, this is a 5 foot high cliff. 5 feet of erosion in 50 years. That's about a foot every decade. That's almost an inch a year of topsoil loss. There's nowhere on earth that soil forms that fast, at least not out of fresh rock. You can build soil that fast if you have the mineral matter and you're just adding organic matter, and I'll show you examples of that later. But in terms of creating soil from fresh rock, there's nowhere that could keep up with that. Now, I hope you're also sitting there thinking, well, Dave, isn't this like a really extreme example? And of course it is. That's why I use it. It's the most extreme photograph I could find to make the point. And the question is, well, what happens if you move out in scale beyond one corner of a single field in eastern Washington? Well, let's look at the potential for topsoil loss across a whole region of the United States, the Piedmont region of the American Southeast, a region that was one of the breadbaskets of the early British North American colonies. It extends from Virginia up here at the upper right, down here to Alabama in the lower left. So we're looking at a color-coded version, the sort of the 4 to more than 10 inches of topsoil loss across the region that's the upland hill country. So we're not talking about the spine of the Appalachians that runs up through there. We're not talking about the coastal plain of the Carolinas and Georgia that runs through there. We're talking about the hill country, the country that's more like the landscape of classical Greece or parts of the Palouse. And you'll notice that there's 4 to more than 10 inches of topsoil loss across this whole region since the advent of colonial agriculture. So how big a deal is that? Well, if you go back and you read the original journals of farmers and plantation owners in this region, they'll report anywhere from 6 to 12 inches of rich black earth on top of their subsoil. So if we could erode off a third to almost all of the topsoil, literally shaving the topsoil off a region that was once one of the breadbaskets of the European North American presence, it puts into perspective what the Greeks and Romans could do with a 1,000-year run at the land with very similar technologies in terms of tillage. This just took a couple hundred years. Think what they could do with a 1,000-year run at their landscapes. It starts to put into perspective the idea that long-term soil loss can actually add up over generations to the point where it greatly impacts the stability of a society. Now, how does that work? Well, it's not just the problem of soil loss, but it's also a problem of soil degradation. These two soils that are up on the screen now are both from an area in North Carolina where this khaki colored soil, the one that it's sort of resting on here, is a soil from a conventional tobacco plantation that's been farmed using conventional tillage and intensive fertilization for the last century or more. And you'll notice that it looks a lot like California beach sand with some crusty salts in it. And that's kind of what it is, but it's 10 million year old beach sand. It's not fresh modern beach sand. This is geologically recycled beach sand. The parent material, or the material the soil was developed from, is beach sand. But this soil on the left that is darker brown, has lots of organic matter in it, it looks like a completely different soil, doesn't it? But it's the same soil. It's exactly, it's literally over the fence from where I dug this soil up. And what's the difference? This soil hasn't been farmed for 120 years. It was a farm that was abandoned because its soil was degraded at that point, and it was let to go back to forest, and over a century or so, the organic matter was added back into the soil. And you can ask yourself as a farmer, which of these soils would you rather be farming? One is a lot more fertile than the other. And this loss of soil organic matter is as big a deal and as important as the loss of the soil itself in many parts of the world. And if you look at how big a deal that is nationally in the United States, as this paper did in the journal Sustainability did a couple years back, one of the intriguing lines in it is that the soil organic matter content, the amount of organic matter, the amount of carbon that's in the soil, in many North American soils is only about 50%. It's half of what it was when they were converted from forests or prairies to farmlands. In other words, with a century to just a couple centuries of conventional farming across North America, we've managed to degrade roughly half of the organic matter that was in the native soils when European farming practices first arrived in North America. So soil degradation is about the loss of the soil, but also about the degradation of the soil. And this example from Costa Rica shows you just how fast this can play out. Because as for writing Growing a Revolution, which we'll get to in a few minutes, one of the things I did is I visited coffee plantations in Central America. And I looked at the state of the soil. These soils are in the same valley. Actually, they're on the same mountainside. The one on the right shows you the soil in a conventional coffee plantation that's been worked for less than 100 years. And you notice mostly this orangish subsoil. And indeed, when you crest the ridgetop to get down to look into this valley, what you see at the bottom of the valley is the river flowing this orange color. It's not a color that most rivers are supposed to flow. You know, we like to think of them as blue. This one flows orange. What's happening is there's a lot of soil loss off of these fields. And you'll notice that if you compare this soil profile, the character of the soil on this coffee plantation to what you have in the jungle, literally next door, just up the hill, what you have is there's still about a foot of thick black earth of topsoil above the orangish subsoil in the native jungle. It took just 100 years, less than a century, really, for this region to lose its topsoil to the practices that they were engaged in. And they have horrible coffee blight problems in this region at present. They're having big problems for reasons that will become, I think, more apparent as we go on. But the point being that soil erosion may be something that we tend to think of as happening slowly, but it is something that can really add up over time to have big effects. So how big a deal is that when we look integrated around the world? Well, one of the things I did in writing Dirt is I went to the library for about 3 weeks when my students were all off in the field and tried to gather up all the data that I could about how fast are the world's soils eroding and how fast does nature build soils, to look at the two sides of that balance and figure out where we are in the world today. And I integrated data from, I think it was about 1,400 different research papers and published it in the Proceedings of the National Academy of Sciences. The citations are at the bottom. If you want to find the data, there's a whole spreadsheet online that you can look at and grab if you want to use it. But what I found is that soils are eroding from tilled farms, from conventionally managed farms around the world at a pace of about 1.5 millimeters a year. Now that sounds like a slow rate, right? Your fingernails grow faster than that. But at that pace, it only takes about 20 years to erode an inch of topsoil. How fast does nature make soil? Well, that blue number down at the bottom, 2% of a millimeter a year means that it takes about 1,000 years to make an inch of soil. Now, I wouldn't put a lot of credence on that 1,000 years being terribly precise. You know, call it, it takes many centuries to make an inch of soil, but it takes just decades to lose it. At that level, these numbers are robust, and therein lies the problem. If we're losing soil faster than we're making it, we're burning through it. And at the rate that we're burning through it, you can actually calculate out the predicted longevity of an agricultural civilization. Now, it's a crude kind of analysis, the kind that you do on the back of a napkin with grad students, but I've given you the data so far that it would take to do it for yourself, and fairly easily. So that net soil loss of about 1 millimeter a year implies that you could erode off a typical ½ meter to 1 meter thick soil, sort of a 1 to 3 foot thick soil, would just take 500 to 1,000 years. So it'd be measured in centuries, you know, more than 5 centuries, less than 10. Turns out, one of the things I noticed when I was writing the dirt book is that's actually approximately the lifespan of most major civilizations outside of major river floodplains. When we think of places where farming has been sustained for millennia, for thousands of years, we think about places like the Tigris and the Euphrates in the Middle East. We think about the Nile River in Egypt. We think about the Tigris and we think about the Indus and the Brahmaputra rivers in India, or the rivers of lowland China. These places all have something in common. They are big river floodplains. And what happens on a big river floodplain? Well, we all know what happens on the Mississippi River floodplain when it floods. It goes underwater, and the water that comes doesn't just bring water. It's full of silt and sediment and cars or school buses or whatever is floating down the river. And recall that rate of soil loss of 1.5 millimeters a year or so, rounded to about 1 millimeter or so. Well, how thick is a single grain of sand? Grains of sand range from a fraction of a millimeter, ½ millimeter or so, up to about 2 millimeters. So average of about 1 millimeter. In other words, if you had annual flooding that laid down just a single grain of sand, you could completely offset the long-term erosive effects of tillage, of plow-based erosion. And that's why you can maintain agriculture for millennia in major river floodplains and in delta environments, because nature has mechanisms for essentially fixing the damage that the plow causes. It's when tillage moves outside of floodplains that you really start the process of land degradation that can really add up to impact human societies. Now, this, of course, motivated the question of, is soil restoration possible? And I started wrestling with the issue of, could we actually reverse the historical pattern that has played out in society after society? And the good news is that this concludes the really depressing part of this talk, because if we look back through history, there are good examples of bad practices adding up over time, but there's also cause for optimism that we can reverse it. And the place where I started becoming an optimist on this actually turned out to be in one of the places where you might not really expect a geologist to do a whole lot of field work. And that was in my own yard, my wife's garden. I had the good fortune to marry a biologist who has a great case of what she describes as plant lust. And she's a major gardener. And we wrote The Hidden Half of Nature together that described her experience in restoring fertility to the garden in our yard, and our experience in researching what was responsible for it, and learning about the microbial life that was really the agents that restored fertility to our yard. So this shows you the yard that became our garden in Seattle. It shows we bought this place back in the late 90s. And when we stripped off a lawn that looked a lot like this lawn over here, was what I like to call an old growth Seattle lawn, about 6 inches of tangled roots that had never been planted with anything else. There wasn't a single worm beneath that lawn. And we did not have terribly great soil. I mean, look at this stuff. It looks like that North Carolina tobacco plantation. Khaki colored soil, hardly any organic matter, hardly any life in it. And we realized that we had the mineral part of healthy soil, but what we didn't have was the biology. We didn't have organic matter. We didn't have the organisms. So Anne decided to embark on what she termed her organic matter crusade. And she started composting and mulching, and composting and mulching like you wouldn't believe, getting wood chips from arborists in the neighborhood, coffee grounds from the coffee shops down the street. Our own kitchen scraps went to a worm bin. The Seattle Zoo has a lottery every year for what they term as zoo doo, which is the composted manure from the herbivores. and you mail in a postcard, and if they draw your postcard, you can show up with your car or a pickup truck and have as much Zoodoo as you want. And by the third time that we'd actually won the Zoodoo lottery, we realized that, you know, it was a bit of a sham. You always win the Zoodoo lottery. They have a lot of it to get rid of. But the point being is that we started adding a lot of organic matter to the yard. We didn't dig it in, we didn't plow it, we just composted and mulched. And this shows you what the effect on our soil over the course of roughly a decade. We started with the soil over here on the left. It had about 1% organic matter. The soil we have over here on the right, in the sort of the best part of our yard now, is up to about 10% organic matter. We've literally stashed tons of carbon in our yard. But what's even more important for a gardener is that we've basically brought the yard back to life, and the plants are thriving. We have a wonderful, gorgeous garden now. And notice the time scale. We basically were able to restore fertility to the land in less than a decade, when that's a pace that could actually match the kind of soil loss that we were seeing in the studies I reviewed previously. So what was really going on? Well, it was the soil food web in action. We were adding the compost and mulch to the land surface, and that was being broken down by things that chewed on it and broke it into smaller pieces. It would get broken down in size to the point where bacteria and fungi were consuming it. Those bacteria and fungi turn out to be essentially little fertilizer bombs. They're full of nitrogen, they're full of phosphorus. They're living organisms that have what's in them. They have in them the elements that it takes to essentially grow new life, you know, with the obvious exception of the carbon and nitrogen that get added from the atmosphere. But point being that all those materials are being shed by plants, all that organic matter is being recycled by life in the soil, and that when larger life forms would consume the small life forms that consume that compost and mulch, their excrement, their manure, if you will, their micro manure, was literally manuring the soil from inside out, and that was the source of the organic matter that was fueling the change in our soil. And as Ann and I dug into this literature, we ran into this word down here, exudates, that really captured our attention. I mean, we all know how carbon dioxide, plants capture carbon dioxide from the atmosphere and bring up water through their roots to build their bodies and give off oxygen. But when I was trained to think of roots as straws bringing nutrients up from the soil, the part that was left out in my graduate education was that plants are actually pushing stuff out into the soil. Whether you want to think of it as dripping it out or pushing it out or leaking, choose your word. But that stuff are known as exudates because it's exuded out of plant roots, and roots are more like a two-way street, a two-way highway, rather than just a one-way path to take up nutrients from the soil. And when we found studies that basically were documenting that some plants would push out up to 30% or more of the compounds that they built through photosynthesis out of their roots, that was intriguing, because why would a plant do that? Well, it turns out that this zone around the roots of plants, a zone called the rhizosphere, which is literally Greek for zone around the roots of plants, that rhizosphere is full of life, and plants are intentionally, if we can grant them intention, they are pushing exudates out into the soil to feed the life in the soil, and they're not doing it just to be good neighbors. They're doing it because they're engaged in what Ann and I termed a biological bazaar, or the original underground economy, where if you blow up this root zone around the root down in the rhizosphere, so the roots are shown in the yellowish orange color, the rhizosphere is that purplish color. It's a zone that's full of bacteria and fungi of life within about 1 centimeter to 1 millimeter of each root and root hair around on a plant. And those plants are exuding compounds out into the soil. And what are they exuding out into the soil? They're exuding things like carbohydrates. They're exuding things like proteins. They're exuding lipids, fats. They're exuding hormones. But carbs, fats, and proteins, what does that sound like? Sounds a lot like food. Plants are pushing food out into the soil, and they're doing it to attract microbial life. It works just the way that if you put out pizza and beer on a college campus, all of a sudden, students magically appear. You can get them to your event that way. It's very intriguing that these life forms around plant roots are doing things with those exudates that then in turn benefit the plants, which is why the plants are doing it in the first place. So what's happening there? one of the papers that Ann and I came across in doing the background research for this book was one that documented that bacteria in the soil were consuming exudates put out by plants and then producing their own metabolites, their own waste products. They were metabolizing the exudates into other things. And those other things, which they would then release from their bodies right around the roots of the plant, because that's where they lived, were things like plant growth promoting hormones. So you think about that system. You have this plant who has the ability to capture energy through photosynthesis, and they're taking a cut of that and they're pushing it out into the soil and essentially outsourcing biochemical processes to the microbes that take what the plants know how to produce and they turn it into compounds that help the plants grow and keep healthy. And there's a whole lot of examples of that. There's also things where the fungi that grow in the soil will essentially link up with plant roots and then they send their fungal hyphae off into the soil to grab things like phosphorus elements out of mineral particles in the soil, or to take phosphorus that had been added as a fertilizer and got turned into a stable oxide. They can break that apart and pull that back out and they'll trade it to the plant for a cut of those exudates. So these biological exchanges are going on are an example of a symbiotic relationship, a mutually beneficial interaction that through which the things that support the life in the soil, all that composting and mulching, we were kind of doing the exudate thing ourselves at the surface of the land, the way the plants were doing around their roots. So the kind of gardening that Ann was engaged in, which was cultivating that beneficial life in the soil indirectly and intentionally, unintentionally, until we researched into it and we started to realize what we were doing and who was doing the real heavy lifting, all those organisms below ground, started to ask the question of, well, it's one thing to be able to restore the soil on an urban lot in a city where you have access to the Seattle Zoo and a whole bunch of Starbucks and so forth for sources of organic matter. But could you do this on real life operational farms that are in different areas around the world? So I started trying to engage on that question, and that's what led to writing Growing a Revolution. And this shows you over here a pair of soils from Ratan Lal's long-term no-till experiments at the Ohio State University, where again, you see this khaki-colored soil they started with. They were able to convert it over the course of a little more than a decade, if I'm recalling correctly, to this darker, richer soil. It's the same soil, neighboring plots. They've just been treated different agronomically for the last decade. And they've been able to illustrate that there are farming practices that one can use that can be profitable, that can rebuild the fertility of the land as a consequence of intensive farming. So I took 6 months from my job at the University of Washington to pursue interviewing farmers around the world. And in fact, one of the first places I went was South Dakota. I'll share that with you a little more in a moment. But what I found in visiting places across North America, in Africa, and in Central America, interviewing farmers who had done to their soil on their farm what Ann had done to our yard, had restored fertility to their land, I found that what they shared in common were that they all had adhered to these three principles that are lumped together under the term conservation agriculture. They all had in common that they were engaged in minimal disturbance or no-till farming practices, and they were engaged. And they also maintained a permanent ground cover through cover crops in between their crops and sometimes in companion crops amongst their crops, and they adopted diverse crop rotations. Why are all these little microbes on the screen? Well, because this is to remind me to say that, if you were to basically try and design a system of farming that would cultivate life in the soil, you would not disturb them, you would feed them, and you would encourage a diversity of exudates, a diversity of plants to provide a diversity of exudates that would feed a diversity of organisms. Imagine, for example, just how dysfunctional an entire city of geologists would be. We'd argue about the nature of the landscape and we'd all starve to death. There is greater flexibility in diverse communities. That's how, towns and cities, we all have different jobs, right? We can do more things that way together. So in any case, this recipe of minimal disturbance, a permanent ground cover, or no-till and cover crops and diverse rotations is a recipe for cultivating beneficial life in the soil. It's also pretty different from what we have tended to teach in mainstream agronomy for the last 100 years, where we've taught intensive tillage, reliance on chemical fertilization, and promoting the growth of just a few crops, 1 or 2 crops, functional monocultures. The general principles behind conservation agriculture translate to different settings. That was one of my big takeaways from writing Growing a Revolution. But what I found is that the specific practices need to be tailored to specific settings, to the specific technological level of the farming communities, the kind of crops that they're growing, the social circumstances that they're in, the kind of soil, not just between farms, but even in different places on a farm. So these general principles seem to translate pretty well, but the specific practices need to be tailored to specific settings. The practices people would use in South Dakota were really different than they were using in Ghana. And that shouldn't be a terribly big surprise. But what I was so enthused about was that it seemed that these general principles seemed to hold across the board. So I'm going to share with you examples of a couple farmers that I visited around the world to investigate this, and that led me to that conclusion. And the first gentleman I visited was Dwayne Beck, who ran Dakota Lakes Research Farm for South Dakota State. And he was very generous with his time and in teaching me, in teaching a geologist about farming practices and the way they had changed. One of the reasons I went to his neighborhood initially was, well, I had met him at a conference, was really impressed with what he was doing and wanted to go interview him, but also the cover. If you look on the cover of my dirt book, it's a Dust Bowl era photograph from South Dakota. So I thought, what a great place to actually start interviews for what ended up becoming the optimistic sequel to the dirt book, than back in that same neighborhood. So when I visited Dwayne, he took me around for a couple of days, showed me the Dakota Lakes and the farmers he was working with. You'll notice the mulch cover from previous crops and the remains of cover crops through here. Through adopting no-till cover crops and complex rotations, progressively over a few decades, as he learned how to make a system that would work in this region, he greatly reduced inputs of diesel, fertilizer, and pesticide, by his accounts when I was visiting him, by more than about half. I mean, when you think about the big expenses on a modern farm for the farmers he was working with, that was greatly cutting some of their really big expense items. So what happened on the income side? Well, compare the yields that they had when they adopted their complex rotations, the minimal disturbance, the cover crops and complex rotations relative to the traditional yield they were getting from their in that area. And you notice the yields went up, not by a whole lot, but the point is their yields didn't go down, but their costs did. And that's a recipe for a more profitable farm. It also helped boost the health of their soil, and that enables them to maintain the reduced level of these inputs over time. When I left Dwayne's place, he was working with farmers up to 20,000 acres. When I left his place, I was asking him, hey, this is like really interesting, but the big problem of feeding the world for the next 100 years is centers on Africa. And I was asking, well, would these practices translate to subsistence farmers on the African continent? And Dwayne said, well, don't ask me, go ask somebody like this gentleman here, Kofi Boa, who runs the No-Till Center for Research in Kumasi, Ghana. I'd also had the fortune of meeting Kofi at a conference and got a hold of him, went to Ghana to visit him. And the first thing I saw when I got out of the truck was his hat. Check it out, got dirt, get soil. The gentleman, obviously, he and I were obviously on the same wavelength. And he showed me what they'd been doing at the No-Till Center in Kumasi, where he's been teaching the farmers in his native village how to move from their traditional slash and burn style of agriculture to a style of no-till with cover crops. They get their diversity in because they're in a different way. They're growing like 6 to 8 different crops in the same field all at once. So they get their diversity sort of all at once rather than in a rotation. And what's happened there is that they have greatly reduced the erosion rate that they were having under the traditional slash and burn style of agriculture, because once you run out of new forest to clear, if you keep slashing and burning the same land over time, you can degrade the organic matter really quickly. You can lose the soil really quickly. Going to this new style of no-till with cover crops reduced the erosion rate greatly. It also greatly increased their yield. Look at what happened to their corn yield. It went from 1.5 tons to 4.5 tons. It tripled. How about their cowpea yield? It doubled. That's as good as the Green Revolution did. But what Kofi was doing is he was doing it without any additional agrochemical inputs, without any patented seeds. And if there's a very simple and compelling reason why the Green Revolution bypassed subsistence farmers in Africa, and that's because they don't have money to buy patented seeds. They don't have money to buy fertilizer. They don't have money to buy herbicide. What Kofi taught them was a different style of farming based on thinking differently about the soil and changing their practices to adopt these conservation agricultural practices. And it transformed the economics of his village. The third farmer I'll share with you is David Brandt from Brandt Family Farm in Carroll, Ohio. He's standing there modeling for you a tillage radish in a field of his cover crops where he's got, I think, 10 or 12 different species all planted at the same time. I visited him back in 2015. His neighbor's soybeans over there across the way are infested with glyphosate-resistant mare's tail weeds, those green things that are showing in between the yellowing soybeans. But what David has done is he adopted no-till practices back in the late 60s when he came back to the US after a stint in Vietnam in the Marine Corps. And then he eventually added cover crops, and then he went to these diverse cover crop rotations. And he was kind enough to walk me through the difference between his operation and sort of the typical operation in the county where he lives. So in his county, full tillage is the norm. People are applying up to 200 pounds of nitrogen per acre, 2.5 quarts of Roundup. The total cost he estimated about $500 an acre in the area back in 2015. Their corn yield was about 100 bushels an acre, and since they were getting about $4 a bushel in that year, that meant that his neighbors were losing about $100 an acre. Even a geologist can tell you that that's a very bad business model. The harder you work, the more money you lose. And I independently verified that in the next state over, I think it was Iowa, in that same year, 24% of the farmers lost more than $100 an acre on their corn. American farmers have gotten so good at growing so much of just a few crops that the prices they get for their commodity crops are low, whereas the inputs that they rely on to produce those crops, those prices have not gone down in real dollars historically. They've gone up, and it's farmers that have been squeezed in the middle. David Brandt, though, he had a whole different business model. He'd adopted these principles of conservation agriculture. So he was not tilling. He hadn't tilled in 44 years. He had to use cover crops for a couple decades, and he's using these diverse rotations for a little while. So he was not doing any tillage, which means he was saving 50% in his diesel bill right out of the gate. He was using about 1/8 of the nitrogen and a little more than 1/3 of the Roundup. He's not an organic farmer, but I started teasing him that he was an organic-ish farmer because he had so greatly reduced his agrochemical use as to be almost certifiable organic. But he was into this for different reasons. He didn't like writing checks for nitrogen and diesel and Roundup. And his total costs for his methods were about $320 an acre. His yields were greatly exceeded his neighbors, and he was making $4 a bushel. At $4 a bushel, he was making $400 an acre when his neighbors were losing $100 an acre. This is what really started turning me into an optimist on this issue, is that it seems that the economic forces are starting to align such that farmers have a very compelling economic rationale for adopting conservation agricultural practices. And that because the more that they can save on inputs without compromising their yields, that makes for a better bottom line, a better profit. So how was David Brandt able to do this? The difference is laid out right there in his soil. So the soil on the left, that deep dark black stuff, is the stuff that we were just standing out in that field with him in. It's got an organic matter content that's back up to about at or above what the native topsoil before the area was ever farmed was. The soil on the right is what his neighbors had. It's very similar to what David Brandt started with back in the 1970s. So you're again going from less than 1% of organic matter to up north of 5% organic matter in just a couple decades. Which soil would you rather be farming? This rich black stuff that has a nice crumb structure and that has good void spaces in it, or this khaki stuff that you can just like smear like wet concrete? The difference in color says it all. It's just like those North Carolina tobacco plantations, and it's just like my wife's garden. The last farmer I'll share with you is Gabe Brown. He's a North Dakota farmer, many of you probably know from Bismarck, and he has been basically adding another dimension to this conservation agriculture recipe, and that is reintegrating livestock into both his prairies through intensive rotational grazing to restore the native prairies that he's been remarkably successful with, but he's also using livestock to terminate his cover crops. So he's basically bringing cows, and this shows you his market garden where he's growing vegetables for his farmer's market operation, and he brings the cows in to graze off the cover crops after the cash crops, and he lets chickens loose to eat the things that seed themselves in the cow patties. And Gabe likes to say that he's no longer paying for fertilizer and pesticides, he's selling beef and eggs. It's a better business model. So what has this done to the soil in that field? This shows you the soil in the field that I was on the right-hand side of the screen a moment ago. We had literally dug it up just moments before I took this photograph, and it's being compared to the soil in his left hand down here. That's the soil from his neighbor's organic farm. And again, Gabe is not an organic farmer, but I don't think he's using any synthetic inputs at this point. He's having tremendous success at rebuilding the health and fertility of his soil. And he's gotten the organic matter content up higher than his organic neighbors. And why is that? Well, there's nothing wrong with the organic practices of his neighbors. They're just still tilling, and that limits the amount of organic matter that you can build up in the soil over time. Again, the basic color difference really says it all and translates into differences in carbon. So this is a slide that I borrowed from Gabe that is from his Grand Forks TED Talk. He basically charts the organic matter content of his soil as he started back in 1993. When he started with no-till, he was down below 2%. And as he added diversity to his cash crops and started integrating cover crops, and then went to multi-species cover crops, and then started integrating livestock into those areas, notice what happened. You went from less than 2% to a little more than 6%. It tripled in 2 decades. This is an incredible change in soil organic matter that is really different than what has happened in many regions of the world where conventional farming practices has degraded it. He even got one field up to a much higher amount, but for most of his ranch, tripling it, I mean, that's still incredibly impressive over the course of a couple decades. So when Ann and I were mulling over Growing a Revolution, we came up with the way to characterize what the recipe for rebuilding healthy, fertile soils is in agricultural practices. And we came up with ditch the plow, cover up, and grow diversity as essentially the slogan behind how you might think to characterize this. No-till, cover crops, and diversity in your cash crops and or your cover crops. What I forgot to tell you is that David Brandt is mostly selling corn, wheat, and soybeans. Those are his cash crops, but he's growing all kinds of other things in his cover crops. So there's different ways to get at meeting each of these principles, but it's the combination that really seems to catalyze the cultivation of the beneficial life in the soil that proves so beneficial in turn to farmers and the productivity and profitability. And you don't just have to take my word from it. You can take the word from someone much more local to you, Jonathan Lundgren from South Dakota. It's an entomologist, and he and one of his students, Claire Lacan, back a couple years ago now, I think it was 2018, the year after Growing a Revolution came out, they came out with a paper in Peer J that looked at regenerative agriculture by comparing cornfields in both farms that had adopted principles like David Brandt and Gabe Brown were using, and then conventional farms not necessarily next door, but nearby. And they did comparisons of the revenue and cost for these conventional and regenerative farms. I think it's 20 paired farms, if I recall, across the American Midwest. And the way you read this graph is that the total revenue is up here at the top of the bar. You then subtract off the expenses in color, and that leaves you with the white stuff on the bottom. That's your net profit. And you can kind of get into the details if you want to see, what is needed in different things. The conventional fields, they're using the fertilizers that color, so they're using less fertilizer in the regenerative fields. They're using less irrigation water. The big thing to notice is that the net income per acre was higher and the net expenses were lower, leaving you a higher profit. So you don't have to just take my word for it that these practices are more profitable. They appear to be playing out in papers that are coming out in journal articles as well. But the thing that was a little more surprising to me in Claire and Jonathan's paper was the difference in the amount of corn pests. And in hindsight, it shouldn't have been surprising, but I'm not an entomologist, I'm a geologist. So in looking at the number of corn pests in cornfields on the regenerative and conventional fields, What you may notice is that there's 10 times fewer on the regenerative fields. The fields that are not using pesticides have fewer pests. They don't advertise that on the label of pesticides for an obvious reason. So what's going on? Well, think about that old, if you've ever had like a course in ecology and seen the graphs of sort of wolf populations and deer populations, or just imagine how those would be in cycle with each other. When there's a whole lot of deer, the wolves are starting to eat the deer and the wolf population goes up. But once they ate all the deer, the wolf population crashes down. Which comes back first? Well, the predators don't come back first. The prey comes back first. So if you think about what a broad spectrum pesticide does to the insects on a farm field, it kills not only the pests, but it will kill the predators of those pests as well. And it's not the predators that come back first. The predators always come back second. The prey comes back first. The pests come back first. And so regular routine overuse, I would call it, of pesticides locks you into a cycle where the pests will always be bounding back and you're not getting the insect predators back because you're taking them out each time. So what are the benefits of healthy soil? The way I like to synthesize this is I put higher farmer profits at the top, because for any kind of farming to be sustainable, it has to work economically or it won't be sustained. And again, this is how I started turning into an optimist on turning the global problem of land degradation around. So I think we're getting to the point where it actually benefits farmers on their bottom line, because they can grow comparable yields with less fertilizer, pesticide, and fossil fuels. And that's a recipe for higher profits. But there are also broader societal benefits in terms of increased soil carbon, all the color differences in the soils that I was just showing you. That relates to carbon taken out of the atmosphere by photosynthesis and parked in the ground. And that's something that, you know, sort of climate activists in Seattle and farmers in the Midwest ought to be able to agree on is a good thing, but maybe for different reasons. It can increase water retention and result in less offsite pollution. The best way to actually reduce offsite nitrogen and phosphorus loading in water bodies and domestic wells and the Gulf of Mexico is to use less fertilizer on fields to begin with. And these regenerative practices allow that. So where are we in agriculture today? As I try and wrap up here, you know, if we look at the first agricultural revolution, it goes back a long ways. This is the Greek goddess of cereal, Ceres, and cultivation and tillage was really the first agricultural revolution. This whole idea of agriculture in the first place was revolutionary. The second agricultural revolution was when we learned about the ideas of soil husbandry and planting legumes and crop rotations. Long before people knew what legumes did for nitrogen in the soil, they knew that it helped the fertility of the land. Crop rotation, these things are not new ideas. Diversity and crop rotations are old ideas. And this quote from Leonardo da Vinci that I'll let you read for yourselves if you want. I mean, where else can you find a quote in science that's as true today as it was 500 years ago? We probably know, we're just learning about the world of life in the soils and how complex and interwoven it is with agriculture. The third agricultural revolution was the mechanization and industrialization that happened in the 19th century in terms of the rise of the fertilizer industry spearheaded by Justus von Liebig. He actually, though, at the end of his career, the gentleman who's basically credited with the rise of thinking up and instrumentalizing synthetic fertilizers, the second book that he wrote at the end of his career argued for building soil organic matter as the key to long-term sustaining of agricultural productivity. The fourth agricultural revolution was that, you know, I lumped the green revolution and the ongoing biotechnology revolution into the fourth revolution, sort of late 20th century, early 21st century. I don't really want to get into or argue the details of was this good, was it bad, all that kind of stuff. It happened and transformed agriculture, but I think that we're basically poised now for what I like to call the fifth agricultural revolution. And that is a revolution centered on these ideas of soil health and building healthy, fertile soils, of returning fertility to the land as a consequence of intensive agriculture. And the kind of practices that I've been describing and I wrote about in Growing a Revolution, I think are the key to understanding how to do that. It's to engage in farming practices that cultivate the beneficial life in the soil that will allow us to actually move back from degrading land, flip that arrow I started with around so that we can basically, as I put in the subtitle of Growing a Revolution, bring life back to the land. And that was meant not as an illusion, it was meant literally. So I'll leave you there in terms of the talk. I obviously recommend the books to you. They're written for non-technical audiences. It's been a joy to actually sort of get to research and dive in and write that material. As a geologist, I never thought I'd be thinking so much and working so hard on issues related to the soil, but it turns out to be a really important issue today that I think there's tremendous opportunities in terms of how to reframe farming practices to rebuild healthy, fertile soils in ways that will benefit both farmers and society at large. So I will stop my sharing there and turn this back over to the next phase. I think we're probably about at break time.
Thank you, Dr. Montgomery. That was excellent.
Thank you.
So for all of you participants, we do have a poll of consisting of 3 questions that we would really like you to take a few minutes and just, or seconds actually, and just answer. It'll help us for future conference planning. And we're probably not going to take too much of a break because we went a little bit over, and it looks like we've got some of the next section ready. And if you want to take a little get up and go break, you don't have to leave your Zoom. You can just leave it on, and we'll just roll right into the next session. And I'll see all of you in the next the chef session. I'm going to buzz on down to the hospital, and we'll talk to Chef Scott. So see you guys for dinner. And Barb, I'll be listening to you on the road.
Thank you so much, David, for presenting tonight. That was so informative and interesting, and a lot to wrap my head around. And it was, but it was just so great with all of those examples, and did make me feel really positive, actually. So thank you for being here, and I hope that we'll be able to see you again. It was really cool too that you had examples from South Dakota. I almost wasn't expecting that. So, but that was wonderful.
Good. And it was legit, totally legit.
Yeah, yes. Great. Well, we have a huge crowd here, so I think everybody really had a great time and was really engaged, and I hope that we can see you again sometime.
You know, I would be glad. I've enjoyed visiting South Dakota in the past and look forward to doing it again once we're doing a little more traveling.
Once we're traveling, great. Thank you. Thanks everyone for being here. We'll have a break.
Kathleen, when are we starting the next session?
We'll be starting in 5 minutes.
Okay, perfect.
Great. Thank you.